So, welcome to this next lecture on vibrations of plates and shells. In the last class I was talking of Raylegh Ritz for a cylindrical shell. Okay. So far I had spoken only on flat structures. So, I am just giving an example of a curved structure over here. Okay. So, as before, if you compute your specified equations from the general set by using these A1, A2, R1, R2 parameters, you will get your stresses and strains appropriate for the cylindrical shell. Then you can form the V max function, and you can also form the kinetic energy max function, and then the Rayleigh quotient, and do your differentiations. Okay. Now, before you do the differentiations, what admissible functions would you choose? Here I am kind of, what shall I say, cheating. I am choosing the exact functions just to demonstrate, or exact mode shapes. I have chosen the exact mode shapes just to demonstrate. Okay. So, the u you choose as A1 cos m pi x over L cos n equal to 0 theta, which is the mode shape. Then A2 cos m pi x by L cos 1 theta, and A3 cos m pi x by L cos 2 theta. I have chosen till 2 in the theta direction. Then V we take as A4 sin m pi x by L sin 0 theta plus A5 sin m pi x by L sin 1 theta plus A6 sin m pi x by L sin 2 theta. Okay. Then W is equal to A7 sin m pi x by L cos 0 theta plus A8 sin m pi x over L cos 1 theta plus A9 sin m pi x over L cos 2 theta. These are the exact mode shapes. Okay. But one thing is, when you do this over here for the torsional displacement, sin 0 theta goes away, this goes to 0. Okay. So, the torsion is uncoupled at n equal to 0. Okay. So, you will not capture that mode. So, what should you do? What you should do, it in order to capture that one mode, you can add, okay, from the other set of modes A10 cos m pi x by L sin 0 theta plus A13 sin m pi x by L cos 0 theta plus A16 sin m pi x by L sin 0 theta. So, these two are not there. So, now if you put this mode in here, you will capture the N0 torsional mode, n equal to 0 torsional axisymmetric torsional mode you will capture. Okay. Then what do? Then you just do whatever the procedure is as before, del Vm del Ai minus omega square del psi m by del ai equal to 0. Okay. Then you form your generalized eigenvalue problem and you solve it. Then you should be able to get the resonances of a cylindrical shell. Okay. For one set of one particular shell, okay, steel, uh, 2 millimeter, radius equal to 0.1, length equal to 0.2, mu equal to 0.3. Results are given in the book. Okay, in the book by Sodal, along with actual formulas for quote unquote exact values. Okay, the third order polynomial is solved. Okay, and those values are also given, so you can compare with your Rayleigh Ritz method. Now, if you are faced with now a cylindrical panel, it is not fully closed in the theta direction. Okay, so it is not closed in the theta direction, it is simply supported here, simply supported here, simply supported here and here. If you are faced with this, okay, instead of cos n theta in the earlier mode shapes, if you put in cos n theta pi by gamma, and instead of sin n theta you put in sin n theta pi by gamma, where this angle is gamma. Okay, you measure 0 or theta in this way. Then the set of modes will now satisfy the simple support conditions on all 4 sides. Okay, then you can do Rayleigh Ritz on these mode shapes or admissible functions and obtain resonances for a cylindrical panel. Okay, simply supported here. And here also on all 4 sides. Okay. Then what? Then in the line of the circular plate and annular plate, okay, suppose you had a plate sector. We measure theta from the center line. This total is 2 alpha. So this is minus alpha and that is alpha. Okay. So if you did this, suppose r square cos n theta, okay, and n was your pi by 2 alpha. That means this is equal to r square cos theta. Okay, so this function theta is minus alpha alpha to alpha. Okay. Now at theta equal to plus minus alpha and at r equal to 0, this function goes to 0, w r comma theta goes to 0. Okay. So this is like a supported sector, it is like a supported sector of a plate, and this is free over here. Okay. So you could use this function and estimate the fundamental natural frequency of this sector. Okay. You should use the circular or polar form of the strain energy. I have given it through a paper, or it is computable from the general form, that also I have given. Okay. That is how you can estimate the natural frequency of a sector. Okay. Now one more thing I want to mention is that there is a paper, there is a journal paper it is titled Prediction of Natural Frequencies of vibrations of rectangular plates. Sorry, it's not, that's not the end of, with rectangular cutouts, Okay. It came out in this journal, Computers and Structures, volume 12, (819) to 823, 1980. In 1980, authors are R. Ali and S. J. Atwal. Okay. This is an interesting paper. Suppose very often you are faced with not normal plates, but plates with cutouts. Okay. You can have a plate with some part removed here or some part removed here. Okay. Or you can have a plate with some part removed over here. Okay. So this paper discusses Rayleigh Ritz method, for such plates, and they do, I think, a comparison. They compare with a commercial package. I forget, maybe ANSYS or computer package. Okay. Now the way they do it, of course, is quite simple. You compute your maximum strain energy, right, over the plate. Let us say the alpha 3 part is done. Okay. Then what you do is you actually compute this strain energy over the material. Okay. That means you set your limits on alpha 1, alpha 2 such that the voids are avoided. Okay. Similarly, in computation of the kinetic energy function, okay, you take the limits in alpha 1, because these are rectangular plates and rectangular cutouts. You take limits in alpha 1, alpha 2 such that you avoid the voids. Okay. Then what you do is you form your admissible functions. Okay. You can use the same set of functions that satisfy the outer boundary conditions. Okay. For example, you can even use Bhatt polynomials based on what conditions you have. Okay. Then you form your del Vm by del Ai minus omega square del psi m by del Ai, these set of equations. Okay. Then you will find that the resonances more or less match with the package commercial code. Okay. Only thing is that this hole size cannot be too big. Okay. There is some rule of thumb. So, hole size cannot be, the void size, the dimensions of the void cannot be too big, voids cannot be too big. Okay. If the voids are too big, then you have to actually satisfy the inner boundary condition, which you are not actually. In this method you are not doing that. You are just subtracting the potential or strain energy of that part and the kinetic energy of the same part. So, you are sort of doing it. Okay. So, it is okay if the size of the hole is small. This is compared to the plate, if the size of the hole is small, it is okay. But once the size of the hole or void becomes comparable to the size of the plate, then there is warping and all such effects come in. So, you have to satisfy the inner free boundary condition over here. Your admissible function has to satisfy, otherwise you will not capture it. So, for reasonable sized voids, this is an open problem. Okay. There is a lot of work in this area to compute vibrations and sound from such plates, but you cannot find functions that satisfy the outer and inner boundary conditions. For example, a function that satisfies the boundary condition here and a boundary condition there, it suddenly has to satisfy a condition on the void boundaries. Okay, you cannot find such a function. I mean, it is difficult. So there are papers, but they obtain the lower modes, lower 4 or 5 modes, but not more than that. So beyond that, the numerical method becomes unstable. Okay, so that is an open problem. But for voids that are not too big, you can try this, and the paper lists results. So you can use the Butt polynomials that I discussed, Butt admissible functions, and you can try this. Okay, without too much details, I am giving you things to try. Now we have not discussed about partial rings, arches. These are difficult problems to find mode shapes, okay, because theta, the in plane and transverse get coupled, and these are not easy to find exact mode shapes. So you can do inextensional approximations or those kind of Donald-Mustarev-Lasov type of approximations to find some results. But so suppose you have an arch like this pi, and it is built in, that is clamped. It is clamped here and clamped here. Okay. So we have seen admissible functions for straight beams. For straight beams we have seen right in the beginning of Raylegh Ritz. Okay. So in the x coordinate. Okay. Now we have the coordinate in the theta direction, it is curved. So you could try for this u theta as sum a1 theta into pi minus theta plus a2 theta square pi minus theta plus a3 theta square pi minus theta square. So try to get a complete set. Okay. So at theta equal to 0 and pi, this goes to 0. Okay. U theta is this motion, u theta is the in plane motion. So at, let us say we measure from here, theta we measure from here, theta equal to 0 and pi. So at theta equal to 0 and pi, these functions go to zeros. So u theta movement is arrested. Okay. Then u3, on u3, okay, u3 there are two things, this is u3 here. At this point this is u3. Then you have del u3 by del theta is also 0. Okay. The slope is also 0, this clamped built into the wall. So you need a function that is slightly higher order to satisfy this. So what do? We take u theta, we start with b1, let us say theta square, okay, pi minus theta whole squared, okay, plus b2 theta cube. Now you start completing the polynomial, okay, plus b3 theta cube pi minus theta cube, etc. Then as usual you formulate your Vm and psi m for the particular coordinates or geometry. and you start your del Vm by del Ai minus omega square del psi m by del Ai equal to 0 set of equations, and you formulate your generalized eigenvalue problem. Okay, so this will give you an estimate of natural frequencies. Okay, so that's as far as the Rayleigh Ritz method that I wanted to share with you. Thank you. I close the lecture here.